Good afternoon, everyone. So I'm honored to be here to present our work, two-factor authentication using acoustics and vision on smartphones. This is a joint work with my colleague Jay and my advisor, Professor Fan Ye from Stony Brook University and Reipeng from Beijing Jiao Tong University. So user authentication on smartphones has a broader applicability user scenarios. For example, but for existing solutions such as the PIN number, face recognition, iris scan, and fingerprint sensors, they all have their own limitations. So the latest art, Apple's Face ID, they pack a set of sensors into a small area on the front panel, but it has high costs, and also it takes precious space. So we ask this question: is there an alternative using existing sensors available? So our answer is yes. So this figure shows the basic idea of our approach. We use the top microphone, earpiece speaker, and the frontal camera as a combination of hardware for authentication. So AccuPrint emits the acoustic signal from the earpiece speaker, which get bounced back from your face. And we extract reliable features from the reflected signals. And these features are combined with the visual features for authentication. So let's look at acoustics. So the reflection signal, it depends on the 3D geometry of your face. And also, it depends on the material of the reflector. So it's hard for you to attack such design using 2D images. However, it lacks the information of 2D visual features. And what's more, so the reflected signal is very sensitive to the relative pose between your smartphone and your face. And on the contrary, for the vision, it has very rich 2D appearance information, and it's robust to different viewing angles or distance due to the vision transformation. However, they can be spoofed by images or videos, and it's subject to the lighting conditions. So to use acoustics for authentication, we have a few challenges here. First, the echoes it's very noisy, and they have large variances because if you hold your phone in front of your face, your hand may move from there to another place. So during the movement, your signal will have very large variance. And second, the echo from the face needs to be extracted reliably. So some clutters around your face may create even stronger echoes. So how do we segment the signals reliably? And third, to train a model for a specific user, we need training data. However, if your hand movements has no constraint, or you move your phone randomly in front of your face, it's extremely hard for you to get enough data to train a reliable model. So how can we do that with limited training samples? So this figure shows the signal we use, and we use a length of 1 millisecond to avoid self-interference, and we're using FMCW, which is continuous wave, using a frequency from 16 kHz to 20 kHz. So the wide bandwidth can give us higher resolution and also minimize the annoyance to the users. And we use Honey Window to increase the SNR. And next, we need to locate the direct path signal, which is the signal from the speaker to the microphone directly. And after that, we need to localize the major echo. So in this step, we just assume your face is plane so that we can find a major echo from your face. And after that, we extend this signal by 10 samples before and after this major echo. So this gives us a depth of 7 centimeters to cover the depth of your face. So when we are trying to locate the echoes from your face, sometimes you will have clutters. For example, there's a wall behind you, so you may have even stronger reflections from the wall. So how can we tell which one is from the face and which one is from the clutters? So to do this, actually we can leverage vision. So this figure shows the distance measurements from both acoustics and also the vision. So basically, if we are using a frontal camera, we can detect your face landmarks in real time so that we can, depending on the distance between the landmarks, we can estimate the distance from the phone to your face. So this figure shows that the results of the measurements when we move the phone back and forth in front of your face. As we can see, we have some outliers here. That's because you may have even stronger echoes from the clutters, so they are causing outliers. So vision, actually, they can provide us a roughly estimate of the distance measurements, but it's robust. But for acoustics, even though it has higher resolution, but you may have outliers. So we combine both of them. We use vision measurements to narrow down the search region so that we can reliably detect the echoes from the face. And after that, as we mentioned before, the acoustic signals is very sensitive to the relative pose from your phone to your face. So that's why we design face alignment. By that, we mean we track the face movement in real time so that we can align your face in a predefined area so that we can confine your movements of the smartphone. So this is very critical for reliable acoustic sensing. So after that, we get the signals. It's still very noisy and it has large variance. So we to extract the reliable features, we leverage convolutional neural network. So we train this model based on a large data set that we collect from about 50 users. And then after we training this model, we remove the last layer to use it as a general feature extractor. So this slide shows the authentication model of our design. Actually, it has two components. So one is the acoustic representation learning. So that's the one-time offline CNN training on PC. And the other part is the two-factor authentication, which runs on our smartphones. So we take all the data. So that's a big data set we collect from 50 users. And we train our CNN offline. Then we just frozen this model and deploy it on the mobile side. When we do authentication, first we extract features from the acoustics. And in the meantime, we do face tracking and landmark detection so that we can do face alignment. And also we can have visual measurements to help signal segmentation. And after that, we combine both visual and acoustic features for the training. And after we train this model, so actually this is the user registration. And then we can use this model for authentication. So how can we deal with the limited data problem? Because if you hold a phone in front of your face, even though we have face alignment now, we still want to leave some freedom of movement so that user has a better experience. So that means you need to collect the data to sufficiently to cover all the possible poses, but that's not realistic. So we propose data augmentation. So it populates the training data by generating the synthesized training samples through the facial landmark transformation and acoustic signal prediction. Basically, the intuition is that we just imagine your smartphone is a different pose, and then based on the visual transformation, we can predict the new locations of the facial landmarks. And also we can adjust the acoustic signal based on the sound propagation law. And then this shows our implementation. We have an Android prototype. So for the Android app, it runs the face feature detection and face tracking in real time, and also the acoustic sensing pipeline and all the machine learning inferences, including the SVM classification and the CNN feature extraction. And also we have the offline training. And so this is our data collection. We collected 45 users from different ages, genders, and skin color. And also we have non-human objects, such as photos or monitors, smartphones, or even sculpture. And for the data collection, we encourage the user to move the phone slowly in front of their face to collect sufficient data. And additionally, we have invited 12 volunteers for joining as new users for evaluation. So this figure shows our CNN features outperforms other commonly used features with an accuracy above 95%. And we also tested different classifiers, and SVM tends to be the best one. And it's also feasible for you to train an SVM on a mobile device. And this is the results on the new users. We have 12 new users, and precision is above 98%, and which means it's highly secure. We only have very few false positive. And the recall is around 90%, which is reasonable. And this figure shows our data augmentation can improve the recall significantly when the training samples are extremely limited. And we also evaluate the performance and the different background noise. And this figure shows the background noise does not have obvious impact on the performance. However, if we do an extreme test, we emit the singular music, playing the music from the earpiece speaker while when we are doing the recognition. The recall drops to 70%. That means you may want to try multiple times for you to get access to your own phone. But this is just an extreme case. And then we do image spoofing test. We use photos or photos displayed on monitors, tablets to attack the system. And it turns out that the pure vision-based face recognition can be easily spoofed, while our two-factor authentication, none of them succeeded. So this shows our system just requires small amount of memory, and it runs in real time with unnoticeable delay for most users. So actually, we still have certain limitations in current stage. The first one is the face alignment. So because we need face alignment, so it can be inconvenient for users for daily use. And we also inherit the limitations from vision, because face tracking is not stable when the lighting condition is not good. And the user appearance change we still need to deal with this problem. And due to the requirement of face alignment, it's hard for us to do the continuous authentication at the current stage. So we do have work in progress. We just replace the vision features with the more sophisticated features from the state-of-the-art face recognition models, so that we combine both features and train a lot of model for authentication. And based on our preliminary implementation and the testing, it even passed the twin test. So our future work mainly focuses on enhancing the CNN acoustic feature extractor by using more data and more sophisticated design. And we also want to integrate our existing acoustic sensing with the existing commercial authentication solutions. And also, for a mature product, we may want to do large-scale experiments. I think that's all for my talk. Thank you.
Okay. Our next speaker is Haitham Hassanieh from UIUC. He's an assistant professor interested in wireless networks, and he's won multiple awards on MobiCom, SICOM, and sort of early NSF Career Award. And he's going to talk about how to detect an eavesdropper, acoustic eavesdropper. And so,
thanks, Wazidar. Good afternoon, everyone. So today I'm going to tell you about how we can detect passive eavesdroppers. This work was mainly done by my students, Anadi Chaman and Jiaming Wang. So unfortunately, both of them could not be here today, so I have to present on their behalf. But it's actually their hard work that got this paper through. So eavesdropping is actually a very long-standing problem. And in wireless networks, it's actually a big problem, because wireless is a broadcast medium. So when you transmit, it goes in all directions. Everyone can hear it. So you have really no control over who listens on the wireless medium. And because of that, basically, we have no way to regulate who can listen and who can eavesdrop on your wireless communication. And that's why, so far, we've taken defensive approaches against eavesdropping. So what's the approach to deal with eavesdropping today? It's encryption. You encrypt your data to prevent someone from decoding it. However, the problem is encryption is not a foolproof solution. So we've seen time after time encryption protocols being broken because of security loopholes. Just last year, WPA2, which we all thought is very secure, got broken. Side channel attacks have been used to break something as strong as RSA. And there's a whole class of other devices which are very low power and cannot afford strong encryption or don't have encryption whatsoever. And these are battery-free devices like backscatter RFIDs and medical implants. And so in this talk, we're going to take a different approach to deal with eavesdroppers. And we're going to ask the question, can we detect the hidden presence of an eavesdropper? Can I know that there's someone out there listening to my communication? And if I can do that, it will take me a long step forward towards dealing with the problem. And it turns out that we actually can do that. And in this talk, I'm going to present a system which we call Ghostbuster. And Ghostbuster can detect the hidden presence of eavesdropper with ongoing communications from transmissions and receivers. And the very nice thing about Ghostbuster is that it does not require any modifications to current transmitters and receivers. So it's a separate device that you add, and it can tell you who's listening. And we've implemented Ghostbuster and tested it on software-defined radios against many different types of eavesdroppers. So how does it work? The key observation underlying Ghostbuster is that even passive receivers that transmit nothing on the wireless medium actually leak RF signal onto the spectrum. So to understand why, let's consider any Wi-Fi card or wireless receiver and look at its hardware architecture. So what you typically have is you have an antenna that's capturing the signal, and then you amplify it, and next you mix it down from passband to baseband. What does that mean? So if your signal is at 2.4 gigahertz, you bring it down from 2.4 to passband, so baseband, so you can do digital processing. If it's at 5 gigahertz, you bring it down from 5 to baseband. And the way you do this is that you multiply the signal with the sine wave at the carrier frequency of operation. So if I want to listen to 2.4 gigahertz, I multiply with a 2.4 gigahertz sine wave. If I want to listen to 900 megahertz, I multiply with a 900 megahertz sine wave. And this sine wave is generated by this local oscillator. So in every receiver, there's a local oscillator that generates this sine wave. And this sine wave is exactly what's going to leak back through the antenna onto the wireless medium. So in every single receiver out there, there's some oscillator that's creating carrier frequency that's leaking back onto the spectrum. Great. But turns out it's not as simple. This RF leakage is extremely weak. In fact, it's orders of magnitude below the noise floor. And that's why it's very hard to detect. So today's receivers cannot detect it. We do not see it, and that's why we don't even try to look for it. So what we need to do is average the noise to bring it above the noise floor and see it. How do we do that? It's actually very simple. All you have to do is take a very large FFT over a very large time window. Let's see how. So let's say you take a few samples and take their FFT. You're unlikely to see anything other than noise. So this is a 200 millisecond window. If we increase it to like a 1 second window, we're actually going to start seeing some leakage. And if we increase it further, and the animation is broken, but we're going to see more leakage. And the further we increase it, the more leakage we're going to be able to detect. Great. So are we done? Do we just take a large FFT, we see who's there, and we're done? Turns out we're not. Because what we really care about is to know who's listening when we're actually transmitting something, right? If we're not transmitting something, who cares? And it turns out in typical networks like Wi-Fi, it's very hard to find a 1 or 2 seconds window where there's no transmissions whatsoever. The AP will just send advertisement packets. So really, instead of this noise signal, what you're going to get all these packets in your time window. And once you take the FFT, instead of seeing this leakage here, you're actually going to see those transmitted signals. So this leakage is going to be really small compared to what is being transmitted onto the wireless spectrum. And in fact, it's orders of magnitude weaker than transmitted signals. And this presents a new challenge of how to extract it when there is transmissions on the medium. But this is not the only challenge. If I'm transmitting something, then someone is listening to it. There's a receiver out there that's legitimate and receiving these transmissions. So this receiver will also create RF leakage onto the spectrum. How can I distinguish it from an eavesdropper? So that's why the new question becomes, how can we extract the eavesdropper's leakage in the presence of ongoing transmissions and leakage from other receivers? And this is exactly what Ghostbuster does. And the first step in Ghostbuster is to null or eliminate the ongoing transmissions. So first, I want to remove whatever being transmitted on the spectrum. And the way it does it is it does this cancellation or nulling in 2 domains, the spatial domain and the frequency domain. How do we do nulling in spatial domain? We use MIMO, multiple antenna devices. So with MIMO, you can actually separate the leakage from the transmitted signals. Now, I'm not going to go into the details of MIMO. You can read them in the paper. It's quite easy. But I want to talk about the other stuff. Because it turns out that just using MIMO is not sufficient to cancel the signal. Let's see why. You're taking an FFT over a very large time window with a lot of packets. And when you do that, what you get is a lot of discontinuities in your signal. These discontinuities will appear at the packet boundaries. They will also appear inside each packet. So inside each packet, there are multiple symbols. And at the symbol boundary, there's discontinuities in the time signal. Now, discontinuities in time domain translate to what in frequency? They actually generate artifacts and spurious frequencies that are very hard to cancel. So really what we need to do is we need to also cancel these artifacts in the frequency domain to be able to recover the leakage. So before I tell you how, let's see where these artifacts are really coming from. So let us consider a very simple case. There's just one frequency. And so when we created the signal, it's just we created a few samples from one frequency and we transmitted them. Now, what did Ghostbuster do? What it did is it took an FFT over a way longer time window. So something like this, way more than what we transmitted. Now, this is equivalent. You can think of it, I don't know if you see the bottom, but you can think of it as a much longer sine wave that we cropped. So as if we multiplied this long sine wave with a rectangle function. Now, multiplication with a rectangle in time translates to what? To convolution with a sinc function in frequency domain. So really, once you take your large FFT, you're actually going to get all these samples from the sink, which are going to create artifacts. Now, you might think this is not a big deal, but really, this is one frequency. The artifacts from all the frequencies in all the symbols in all the packets are all going to add up. And that's going to make them very hard to cancel. Right? So not just one sync function. We have all frequencies, all symbols, all packets. So how can we cancel these artifacts? What we need to do is for every frequency to be able to estimate its position in the continuous Fourier domain. So this is what we called off-grid estimation of frequencies. So the way we do it, so if we can estimate its off-grid position, we can model the sink, model the artifacts, subtract them out. And so the way we do it is by solving this optimization function. Don't worry too much about the math. Just think this Fk is the frequency position, and Ak is the coefficient. And the way you would solve this is you would fix the positions and solve for the coefficients. And this is just a weighted least squares problem. It's very easy to solve. And next, you will iterate back and forth. You will fix the coefficients and solve for the positions. Now, unfortunately, this is not a convex problem. But what we show in the paper is that if you have really good initial estimates of the positions, which we do, the problem becomes convex. And you can solve it using gradient descent. Great. So now we know how to null the transmissions. But we still have one question, is that there is other receivers out there that are also leaking onto the spectrum. So how do we deal with them? What we're going to do is we're going to leverage something called carrier frequency offset between the different receivers. And what this means is that no two receivers out there are identical. The oscillators will create sine wave at slightly shifted frequencies. If we take a short window, we won't see this. We'll see one leakage. But actually, if we take a long time window, we're actually going to see multiple peaks from different receivers. They're going to separate out. So if we know how many legitimate receivers there are out there, we can know if there's an eavesdropper just by counting the number of peaks. Great. So I'm going to quickly tell you a bit about our implementation and results. So we implemented Ghostbuster and USRP software radios. For the eavesdroppers, we used Wi-Fi cards and USRPs. And there's a lot more implementation details, which I'll leave for the paper. The first result I want to show you is that Wi-Fi cards actually leak. So what we did is we took all these Wi-Fi cards, we placed them in monitor mode. So this way, they will never transmit anything. And then we measured the leakage by taking a 1-second FFT window. So on the y-axis, you have the SNR of the leakage. On the x-axis, you have the different chipsets in these Wi-Fi cards. And these chipsets come from 3 manufacturers, Broadcom, Intel, and Atheros. And they cover a wide range of hardware architectures and Wi-Fi protocols from 802.11a to AC. So if you operate in the 2.4 gigahertz channel, this is the leakage you're going to see between 7 and 23 dB. And if you operate in 5 gigahertz, this is the leakage you're going to see. Now, some of these cards just don't support 5 gigahertz. Now, it's telling me the time is out, so I'm going to just quickly summarize the rest of the results in one slide. So basically, what we show is if Ghostbuster can detect Wi-Fi cards eavesdroppers up to 7 meters away, and USRP eavesdroppers up to 14 meters away. And this is because USRPs are made of discrete components, so they leak much more. But this result can be significantly improved in one of 2 ways. Either you take larger time windows, or you use larger MIMO. So instead of 2 MIMO, you can use 3 MIMO or 4 MIMO. And what we show is basically, in the presence of ongoing transmissions and other receiver, the accuracy of detecting the eavesdropper is 95% with 1 receiver and 89.9% with 3 other receivers out there. And so to conclude, I presented a system called Ghostbuster that can detect the hidden presence of eavesdroppers in the presence of ongoing transmissions and other receivers without requiring any modifications to the transmitters and receivers. Of course, there's a lot of future work to be done, and some of the questions are, what if the number of receivers is not known a priori? How can we reduce computational complexity? We're taking 10 million point FFTs here. Can we localize the eavesdropper? Can we use the MIMO antenna to say which direction the eavesdropper is coming from? But not only there are other questions, it opens the door for other applications. So potentially you can use this to detect remote explosives. You can use this to improve carrier sense. If I know who else is listening out there, I can improve my carrier sense algorithm. I can use this to synchronize clocks of distributed receivers. So with this, I'm going to stop. Thank you.
The next speaker is Viet Nguyen from Rutgers University, working with Professor Marco Guster. And his interest is in pervasive communication, visible light communication, and so on. He's going to talk about body-guided communication today.
Okay. Good afternoon, everyone. My name is Viet. I'm from Rutgers University, and today I'm going to talk about our research on body-guided communication, a low-power, highly confined primitive to track and secure every touch. This is a collaborative work between Rutgers University and University of Colorado at Boulder. Okay. So nowadays we have increasing number of devices, from the small Amazon Dash button to a small TV remote controller to smartphones and tablets we regularly use every day. In many cases, the interaction will only be a few touches before we move on to another task. So the conventional user identification and authentication, for example, like the password and the fingerprint sensors, could quickly become an overhead to users. So, and in addition, there is a common need for multiple users to work on the same device, for example, in workplaces, in hospitals, and in classrooms. Ensuring the authorization and accountability is particularly challenging in these environments. So for this usage scenario, it is desirable to have a convenient yet secure user identification and authentication technique. So the existing user identification and authentication techniques have several disadvantages. Some of them, for example, RF and NFC, they are vulnerable to man-in-the-middle attack because it is difficult to confine the signal in because of the omnidirectional property of the wireless signal. And there's some work on touch-based authentication, but they have low data rates, so they cannot do per-touch authentication. And recently, there's some work on vibratory communication in order to transfer credential from user wearable token to the device using vibration signal through the human bone. This kind of work can can associate the user code to every single touch. However, they consume a lot of power because of the mechanical vibration of the small motors. So in order to create a more convenient and low complexity solution for authentication, we start with two observations. The first one is that nowadays we increasingly use wearable devices. For example, wristbands and rings. These devices are good for storing users' credentials because there is less chance that the users can misplace them. And they have the nice property that we are going to use is that they are in direct contact with the user's body. And the second observation is that most interactions are through touch, though the human body can act as the temporary channel between the wearable token and the touch device. So that leads us to the key idea of this work, is that we will try to create a body-guided communication system that will confine the signal to only a few centimeters around the hand, and it will achieve the high data rate high enough data rate to transmit a complete authentication code to every touch, on every touch. And it will achieve the two above points with a very low power. Before we go into this communication channel, let's take a look at research on on-body communication, because it has the same goal of transmitting a signal from a body part and to another body part. So in on-body communication, there are two common coupling types. One is capacitive coupling and the other is resistive coupling. So in both of them, they require two electrodes for transmitter and receiver. And for capacitive coupling, one electrode is in direct contact with the human body and the other electrode is floating. For resistive coupling, both electrodes are in direct contact with the human body. For the capacitive coupling, because it requires the capacitive coupling return path, so the path loss is much more dependent on the surrounding environment, which is not a desirable property. So that leaves us with the resistive coupling. So in resistive coupling, most of the signal will go between the two electrodes of the transmitter, and but a small part of the signal will go across the two electrodes of the receiver and can be picked up. The property of resistive coupling is that the received signal will decrease when the receiver moves away from the transmitter, and the received signal will be higher when the inter-electrode spacing is longer. Okay, so there are some challenges in applying the resistive coupling to our problem of transmitting a credential from the touch token to the device. The first one is that because the fingertip is small, the two electrodes on the touch device can only be separated by a few millimeters. So that will significantly decrease the received signal at the touch receiver. The second point is that it is not desirable to have every touch surface to made of conductive material. In many cases, it is more easier to hide the electrode behind a non-conductive layers, such as plastic and glass. That means that there are no direct skin contact for the electrode on the touch receiver with the fingertip. So in order to overcome these challenges, we propose the body-guided communication. The key difference in our technique is the combination between the direct skin contact at the transmitter and the double capacitively coupled at the receiver. So the two electrodes inside the transmitter is powered by an AC signal power generator. And inside the human body, there are conductive tissue which are separated from the electrode by a layer of skin's epidermis. And we model these skin's epidermis by a parallel pair of capacitor and resistor. We also model the impedance between point A and point B between in the conductive and under the two electrodes. And so most of the current will go in this major path between two electrodes of the transmitter, but a weaker current path will run through the finger and through the touch device. And this minor path can be modeled by a tissue impedance between point B and the fingertip and the two capacitors CFF and CX. And CFF is the capacitance between the fingertip and the front electrode, and CX is the capacitance between the reference point and the body. And CX will be connected through the last impedance to the point A and effectively closing this minor path. So by experiments, we found out that when the finger moves away from the touch surface, this CFF on the minor path, CFF will have the highest impedance. So that is because of the high permeability of the air and the small area of the fingertip and the front electrode. So this high impedance will prevent the current going to the touch device when the finger is moving away from the touch surface. So that effectively provides us with the ability to do touch association and for per touch authentication. Okay, so now let's look at the wearable design. So in order to maximize the received signal at the touch receiver, we want to put the transmitter as close as possible to the touch device. So there are two positions on the where we can put the touch device, the touch token, which is the smartwatch, the wristband, and the ring. So for both of these devices, we put the two copper strips on the two sides of the band and try to maximize the inter-electrode spacing within the size. So these are the two prototypes that we made, one for wristband and one for index finger ring. But because our wristband is much more worn than the index finger ring, so in this research we focus on the smart wristband design. Okay, so so for the design of the electrodes on the touch device, so we consider two example design. One is for IoT device and one for the phone. For the IoT device, we put the electrode behind the non-conductive layer, and that layer can be 1 millimeter thick, and the size of the electrode is about 1 centimeter square. For the phone, because the device thickness can be 1 centimeter, so we increase the size of the electrode to be nearly the size of the device. So, and the receiving electrode is connected to the receiver, and basically the receiver is trying to down convert the signal from frequency F0 to 5 kilohertz, and this 5 kilohertz signal will be sampled and decoded by a microcontroller in real time. So this is an illustration. So in this experiment, a user will wear the wristband and then try to touch the device multiple times, and the transmitter will modulate a 128-bit identification code using on-off key modulation with the carrier frequency of 150 kilohertz. And here you can see this is the output 5 kilohertz, and here you can see that when the finger touches the device, the 5 kilohertz signal increases, and when the finger moves away from the device, it decreases. And when we zoom in this red area, we can also see the on-off keying, the identification code from the on-off keying modulation from the touch token. Okay, so now let's go back to the three main advantages about technique. The first one is that this technique is able to highly confine the signal. We measure the received signal at an electrode that is over a small distance over the wearable touch token, and also measure the received signal at the intended receiver. So here we can see that when the transmission voltage is about 3.2 volts, the received signal at the intended receiver is much higher than the adversary receiver, and the signal at the adversary receiver is decreases with distance. But here you can see that the received signal at the intended receiver is unnecessarily high. We want to decrease the transmission voltage until the received signal at the adversary receiver is under the noise, but the signal at the intended receiver is still decodable. So that is what we do. We try to decrease the signal transmission voltage to 0.4 volts. And here you can see that with transmission voltage of 0.4 volts, with this pink light, the received signal at the adversary receiver is under noise, just under 1 centimeter, but the received signal at the intended receiver is still 20 dB above noise. And here, and we see that independent of the transmission voltage, with a given position of the adversary receiver, the difference between the signal of the intended receiver and the adversary receiver is roughly the same. So we define the signal advantage as the difference between these two signals and use this signal advantage to define how highly confined the signal is. So we also consider other scenarios in which the adversary can eavesdrop on the body-guided communication. The first one is direct skin contact, for example, when in a close collaboration setting. The second scenario is when is the indirect contact through a conductive surface. For example, two people are leaning on the same metal doors. The third scenario is when the adversary is trying to hide a receiver under non-conductive material, for example, the metal base of the table. So we did measurements, and we found out that the signal advantage is always above 10 dB. So there's a note here is that for RF or NFC, because of the omnidirectional property of the wireless signal, we cannot achieve positive signal advantage. The second advantage is the per-touch authentication and identification. So we are able to deliver on 28-bit for 100% accuracy for for touch above 300 milliseconds. Yeah, the last one is the last advantage is that this method has low power consumption. So our method is able to achieve 3.9 microjoule per bit, which is 2 orders of magnitude lower than vibratory communication. And RF and NFC, it has a lower power consumption, but it has it is susceptible to eavesdropping, and it is unable to associate the touch. And we also mentioned in the paper that the theoretical limits of our technique is 90 nanojoule per bit. So in conclusion, we propose a body-guided communication method for securing every touch interaction from users. And we show 3 advantages of our technique. It is more secure against eavesdropping than other wireless method, and it has low power consumption, and it provides per-touch authentication. That is the end of my talk. Thank you very much for your attention.
Our next speaker is Hatian Deng, a fourth-year PhD student at University in Purdue, supervised by Professor Xunyi Peng, and works on the area of mobile networking, more specifically using device-side intelligence to secure and improve mobile network performance. And hopefully in a few seconds we'll be able to start. There you go, just in time.
Thank you for the introduction. Good afternoon. I would like to present our work, which is CEIVE, combating caller, which is a calling-only solution to fight against caller ID spoofing. This started with a real story. One day, my professor received a phone call from Chinese consulate. It claims that she was involved in a money laundering issue and asked her for banking information. Yes, it was scanned. Professor realized that, and there was no money lost. But someone didn't know. He lost $3 million in this June. Not only him, there are many other victims. So the imposter scan has been reported in many places, including FCC, FTC, Chinese Embassy, the Washington Post, CBS. And in the United States, the Federal Trade Commission has confirmed that imposter scan has become the top fraud again in this year. And it is estimated that 1 out of 5 American people suffers from imposter scan. And it is, there is average $274 lost, and it increased to $720 lost. So imposter scan is a big threat to people's daily life, and it was growing at an alarming rate. It is not only a US problem, but also a global issue. There are news reported from many other countries. So all these are caused by caller ID spoofing. To understand why it happens, I would like to introduce a little bit of background about how we set up a phone call. It is very simple. Take 3 steps. The caller Alice wants to make a phone call to caller Bob, so it needs to send a call setup request which contains the caller ID information, which is usually the phone number of Alice. And after that, more call setup signaling messages are exchanged between them to establish a call session. After this, a voice conversation can be started. However, a malicious user, Eve, could easily alter the caller ID contained in the setup request. For example, Eve can use Alice ID, then spoofing is made. Actually, there are so many public tools available that anybody can easily launch a spoofing attack within seconds at no cost. However, defense spoofing is very hard. There are 3 types of solution proposed. One of them is using a global certificate authority between Alice and Bob, but this one requires a heavy deploy requirement and needs upgrades on both caller and caller's carrier network. There are also change and response solution methods which tries, but this one also requires changes on Alice and Bob's side. There are also some caller ID applications which they put efforts on trying to tag a scam number, but this solution is based on phone number search and user report, so it won't work for a new scam phone number at the beginning. So what solution do we really need? What we need is a caller-only solution that requires, without requiring any updates on the existing telephony system. Can we do that? Yes, we can, and here is the CEIVE's basic idea. So when Bob receives an incoming call from Alice, Bob has no idea whether this call is really come from Alice or just spoofed by Eve. So, but what Bob can do is he can make a call back to Alice. Since the networking is not compromised, this call will definitely reach Alice. And then Bob can try to verify to see if the same party Alice is involved in both call sessions without requiring any response from Alice. This is done by comparing the call state of caller and Alice. So in this example, if Bob receives an incoming call and he can know that the caller is in dialing state, and through the authentication call, Bob can learn that Alice is currently idle, then we can see the call state of Alice and Eve are not the same. Then spoofing is detected. So the key question here turns out to be, how can we infer Alice's state using Bob's view only? This is not simple. We tried all the information we can get using from the Android operating system, like call state, precious call state change, system logs from caller application. But all this doesn't work because they are all related to local device state, which is Bob's call state, not the opposite party Alice state. In fact, we found that we can use the call setup signaling message to infer the call state of Alice. Today's 4G phone use 2 types of call technology. One of them is voice over LTE, which uses IP data packet to make a phone call. Another one is CS4 backhaul, which uses the traditional circuit switch to make a phone call. Our study shows that both of them are working, and I will use VLTE to illustrate our idea. So let me use some example to show the feasibility study. Say we have Alice and Bob are both using T-Mobile voice over LTE, and we will consider 3 scenarios. We want to see that if the signal message will be different when Alice is at different state. So the first case is the normal case. So Alice is the real caller, and it makes a phone call to Bob, and Bob makes a verification call back to Alice when Alice is in dialing state. So let's see what we observed in Bob's side. So first, there are some common signaling messages which are used for all SIP call. And then we will observe that Bob will see a 180 ringing message. And also, Bob will see the 200 OK invite as a response to the invite message to indicate that the call session has been established. And Bob will send a bye message to end this call. Let's see what happened in other cases. If Bob makes a callback, but Alice this time is in idle state because Eve is spoofing Alice's caller ID. And this time, we will see some different message. And in the last case, when Bob makes a callback to Alice, but this time Alice is in connect state, this is the signaling message we observed. If we comparing these three states together, we can see clearly that we can observe different signaling messages when Alice is in different states. So this gives us confidence that through the call set signaling message, inferring the call state of Alice is possible. So now I can give you a general procedure of how CEIVE works to detect a spoofing attack. So the idea is when Bob receives an incoming call from Alice, he makes an authentication call to Alice directly and keep monitoring the signaling message exchanged. Then, using a pre-learned call state classifier, CEIVE tries to infer the call state of Alice, and given both call state of Alice and the true caller, we can make the spoof detection. So however, things are not that easy when we try to extend to more carriers. The reason is because although the standard stipulates the mechanism, but it still leaves options for vendors and the carriers. What I mean is that carrier could have their specific implication. For example, Bob could observe different call setup signaling message when Alice is in the same state but using different carriers. For example, here, when Alice is using AT&T CS fallback, Verizon VoLTE, single line landline, we can observe totally different signal message, even Alice is in the dialing state. This leads to a challenge, which is the call state ambiguity. That means Bob could observe the same signaling message when Alice is in different call states. For example, here, Alice using AT&T CS fallback, but we can see in idle and connect state, we observe totally the same, exactly the same signaling message. And that will make it hard for CEIVE to accurately infer the call state of Alice. This is fatal to CEIVE. Another challenge is advanced attack. You may think about what if Alice is dialing somebody, or even worse, Eve could try to manipulate Alice's call state by making another call to Alice when attacking Bob. In this case, Bob will see that both caller and Alice are in dialing state, and then there is no way for us to detect the spoofing attack. So to solve these two challenges, CEIVE is equipped with special design in the call state classifier and the spoof verifier modules. So in the initial training stage for call state classifier, we extend the call state label to a unique combination of not single state, but single or multiple states, call states, and also including the caller and the call list carrier and the call technology information. So for example, after we use some domain knowledge to extract the key pattern of signaling message, we have these 5 patterns. P1, P2, and P3 are observed when Alice is in dialing state. P4 and P5 are observed when Alice is in connected state. The issue is P5 is also observed when Alice is idle. So this is the call state ambiguity. How can we solve it? So the idea is we make sure that a unique signaling pattern can always match to a unique label. So the idea is that in P5, we match it to a label combination with both connected and idle state. So this can guarantee that a unique pattern can always match to a unique label. And I will show how CEIVE can benefit from this approach later. So in the spoof verifier module, CEIVE took a 2-phase verification strategy. The idea is that when Bob received the phone call and device starts ringing, CEIVE made the first verification call. And when Bob answers this call, we make a second call. So this means that the caller state in phase 1 is dialing state, and the phase 2 is connect state. And this table summarizes the possible call state of Alice, and we can see C1 is the normal case, which means dialing in phase 1 and I connected in phase 2. And we can see C2, C3, C4 is the basic attacking mode, C5 to C7 is the advanced attacking mode, and in all these cases, none of them have exactly the same state compared with C1. That means a 2-state verification strategy is already enough for us to make spoofing detection. So in each one-run verification, CEIVE will keep monitoring call set signaling message and end the authentication call as soon as possible once we finish the call state inference. And given the call state comparison result, CEIVE gives 4 types of output. So the decision tree logic behind how we give this 4 outputs is based on this. If the call states are not matched with each other, then spoofing is directly detected. If they are matched with each other, we check if it's the last phase. If not, we give to be continued output and move to the next phase. If yes, we check if there is call state ambiguity. If no, the call ID is verified. Otherwise, we cannot make the decision. So the two-phase strategy not only solved the advanced attack, but also helped to reduce the call state ambiguity. The idea looks like this. Say we have the following inference result. In phase 1, Alice is inferred as can be either connected or dialing. In phase 2, it could be idle or connected. But given the extra information we have, we can find this case could only happen when both Alice and Bob are using carrier 2 voice LTE technology. So this can help us to get accurate inference about call state of Alice and make spoofing detection. CEIVE also includes other components, including relearning about new carrier to support new carriers, timer settings to make sure its responsiveness and friendliness. And also we have smart triggers to guarantee, to avoid unnecessary verification for like numbers contains in a user context list. And also avoid a call loop if both Alice and Bob have CEIVE installed. So now I will give you the evaluation result. So go back to that day. If a user has CEIVE installed, it can detect the consolidated scam. So I will give you the accuracy and the delay of CEIVE. So in accuracy, Bob uses voice over LTE technology, and we consider Alice to use all 4 US major carriers, and also including 1 single line landline. So we test against all 7 scenarios, and we can find that CEIVE can achieve the 100% accuracy when it can give a spoofing detection. And you can see in C1 and C7, for some of the carriers, CEIVE cannot make the decision because the call state ambiguity, which is that CEIVE cannot differentiate the idle and connect states. It also worked for CS4 back. The result is similar. And here, let me show you the user friendliness and the responsiveness. So we measure the phase 1 verification time since the device starts ringing, and the phase 2 verification time since Bob answered this phone call. So for the first phase, the completion time for voice over LTE technology takes about 4 to 10 seconds, and it takes 8 to 10 seconds for CS4 backhaul. This is because CS4 backhaul usually takes longer time compared with voice over LTE. And if we consider 2 phases together, we can see it takes about 16 seconds for voice over LTE, and for CS4 back, it can finish within 19 seconds, no more than 23 seconds. So this result shows that CEIVE can give us timely verification result and prevent the user to get any loss happen before, to prevent the user have any loss. So there are also, we have to admit the limitation of CEIVE that it doesn't work when in the case of there is a multiple line telephone number, because we observe the same signaling message and there's no way for us to differentiate the real call state. So in summary, CEIVE is a call-only solution which uses a call capability only. And we formulated the design as the inference and verification problem, and exploit the call setup signaling message to infer the call state of Alice and make the spoofing detection. Our result shows that CEIVE is a practical and effective solution. And thank you for your time.
So the next speaker is Gay Wang from Xianyang University, and she's a visiting student at UC Santa Cruz, and her interests are in wireless sensing, RFID, and security. Please go.
Thank you for the introduction. It's my honor to introduce our work towards replay resilient RFID authentication. This is a joint work with Professor Chen Qian from UC Santa Cruz and Jinsong Han from Zhejiang University. Battery-free wireless communication, in particular passive RFID, has been widely used in many applications, such as logistics, entrance control, and so on. In those applications, device authentication is one of the most important problems. It is to validate whether a device is indeed the legitimate one that has been registered in the system. However, many existing authentication methods have their own drawbacks. Basically, for commercial protocol, the reader authenticates each tag by scanning its ID. The method does not need any hardware or protocol modification. However, if the attacker utilizes a counterfeit tag that uses the same ID with the legitimate one, the reader cannot tell it. So it is not a good solution for our RFID authentication. To this end, many researchers propose cryptographic-based method. They assume that if the tag can support cryptographic function, it can encrypt the time-varying key sent by the reader. This type of authentication method can defend against almost all major attacks. However, the limited computing capability of ultra-high-frequency passive RFID tags restricts the execution of cryptographic functions, and replacing all the deployed tags may also induce considerable labor and economic cost. Therefore, physical layer authentication methods were proposed. Compared with cryptographic-based method, physical layer authentication method does not need any hardware or protocol modification. It authenticates tags by scanning it, by analyzing their physical layer features, say hardware fingerprint. Due to the manufacturer imperfection, different tags have distinguishable difference on their features, physical layer features. So attacker cannot use a random select tag, counterfeit tag, to play as a legitimate one because its physical layer feature is high probably different with the legitimate tag. Though physical layer authentication method can successfully defend against attacker counterfeiting attack, it is vulnerable to signal replay attack. In a survey called on physical layer identification of wireless devices in 2010, the author said signal replay makes the attacker frames almost indistinguishable from the general frames. Whether such impersonation detection is feasible is an open question. Oh, I'm sorry. Is there any physical layer method that can defend against the signal replay attack? Our answer is yes. We propose HuFu, the first physical layer authentication method that can defend against the signal replay attack without no hardware modification. Before I introduce our design, I first talk about what is HuFu. HuFu, also called Tagliatelles, were authentication seals used by ancient Chinese emperor to dispatch and command the army. It has two pieces. The right piece was returned by the emperor, and the left piece was issued to the general. There is a famous historic story about HuFu. In ancient China, a man called Lord Xingling was told that his hometown was attacked by the enemy, so he had to ask his friend, a concubine of the emperor, to steal the right piece of HuFu. After pairing the right piece held by the emperor and the left piece held by the general, Lord Xingling moved the army and finally saved his hometown. Similar with HuFu in ancient China, we also employ two tags. We have two basic ideas. First one is the inductive coupling of the two tags. Another is the signal randomization. Now, let's see the overview of HuFu. Besides the RFID reader, we also utilize an additional tag called left tag as authenticator. And each user holds an additional tag called right tag. If we inventory the two tags separately, the two tags will transmit the uncoupling signal UL and UR respectively. When a user who wants to authenticate his right tag, he or she should put the two tags in a close distance. In this case, the two tags will inductive coupling with each other, and their transmitting signal will become the coupling signal CL and CR. We also ask the reader to send a random signal ST that varies with the time t. The random signal will hide the backscattering signal of the tag. In this case, the attacker is even unable to tell whether a tag is transmitting or not to mention or term the physical layer signals. Now, let's see how does the two mechanism work on defending against most attacks. First, when an attacker uses a counterfeit tag to cheat the system, say the counterfeit tag T'(C), not only the fake tag, but also the left tag signal will show distinguishable difference with the legitimate features. And if attacker records the coupling signal and replay it at the authentication site, the left tag does not enter the coupling state and will still transmit the uncoupling signal UL. In this case, the reader will detect the existence of the attacker. Hufu can also defend against a signal compensation attack. Signal compensation attack refers to that the attacker sends a well-calculated signal to compensate the current transmitting signal to an expected one. However, signal compensation to Hufu is real difficult. The first reason is that the coupling signals are protected by the one-time random signal. The attacker cannot overturn the raw coupling signals. Another reason is that, according to the protocol, tags will randomly select one slot to respond. As a result, the success hit rate of the attacker will be no more than 20%. Note that in our system, if there exist uncoupling signals of the left tag, we can find out the attacker. So Hufu can also detect a signal compensation attack. Last but not the least, Hufu can defend against brute force attack. That is because the attacker does not know the valid feature, even if the attacker knows the feature extraction algorithm. As a result, attacker has to pay non-trivial expenses on guessing or simulating the valid features. Hufu have two typical applications. The first one is static case, such as entrance control. Another case is called dynamic case, such as baggage claim. For entrance control, the left tag works with the reader as entrance guard, and each user who wants to open the door should show a legitimate tag, red tag. And for baggage claim, each user holds two tags. The left tag is pasted on their baggage, and the red tag is pasted on their ticket. The passenger first registers his two tags at the departure and authenticates his ticket to pick up his baggage at the destination. The main difference between the two cases are whether the device and authentication places are the same. In fact, Hufu is robust to device and environment diversity. More details can be found in our paper. We have two main modules in our design, namely signal preprocessing and feature extraction. Let's see the propagation process between the reader and the tags. The reader sends a random signal ST to the tags, and the environment parameter of the downlink channel is denoted as gamma. Due to the inductive coupling, the backscatter signal XT will be influenced by the hardware characteristic H, and the downlink environment parameter can be denoted as gamma prime. So the received signal can be denoted as PT, which is polluted by the environment parameter, the random signal, and the Gaussian noise. We cancel the Gaussian noise and remove the random signal. More details can be found in our paper. Here is an example of our signal preprocessing. The figure shows the communication between the reader and the text. And the signal in the red rectangle are the randomized carrier waves. If we zoom in the red rectangle, we will find that the random signal can close the text backscattering signal. After our signal preprocessing, we find that text response can be successfully extracted after our signal preprocessing. We extract two environment and device-independent features, namely coupling feature and authentication features. The coupling feature is to verify whether there exists a tag, not a replayer, that is sending the signal. We also propose two authentication features. Note that both of the two features are insensitive to environment and device changes. Finally, let's see our evaluation. We implement HuFu with an USRP N210, and we utilize 150 tag pairs in total. We first evaluate the authentication quality of HuFu. We compare HuFu with three existing mechanisms. We found that in static case, HuFu can achieve up to 95% accuracy. And even in dynamic case, HuFu can achieve up to 90% accuracy, which outperforms all other three mechanisms. We also evaluate the bit error rate of the eavesdropper after signal randomization. As shown in the figure, the CDF of the bit error rate for the eavesdropper in static and dynamic cases are extremely close to 50%, which is very similar to that of random guess. In other words, HuFu provides almost no information of the bits of the tag replaced. We also evaluate the impact of some practical factors, such as the separate distance between the two tags, the intersection angles of the two tags, and the outside temperature. Let's see the figures. We found that both of the false accept rate and the false reject rate for 1 centimeter to 3 centimeter are all smaller than 10%. Hence, by slightly moving the right tag, the results are still reliable. We also evaluate the performance of HuFu when the right tag is not fully parallel to the left tag. We find that the false accept rate and the false reject rate are no more than 10% when the angle is between -8 to 8 degrees. According to the result, we can safely infer that an intersection angle smaller than about 8 degrees may not impact the result significantly. The outside temperature may also change the hardware characteristic of the RFID tags. As shown in the figure, we find that when the temperature is smaller than 8 degrees, HuFu has stable accuracy. Now, let's quickly conclude our work. HuFu is the first physically authentication method that can defend against a signal replay attack. And HuFu is also robust to the device and environment diversity. We implement a working prototype of HuFu and achieve high authentication accuracy. Thanks for your attention, and you are welcome to contact us.
Our next speaker is Dan-Hik Hang, a PhD student at Arizona State University in Yanchao Zhang's group, and he's going to talk about proximity proof paper. So thanks.
Thanks for introducing. Hello, I'm Dan-Hik Hang from Arizona State University. Today I want to present our paper, Proximity Proof, Secure and Usable Mobile Two-Factor Authentication. This is the joint work with Yiming Chen, Tao Li, Rui Zhang, Yanchao Zhang, and Terry Hedgepage. Mobile two-factor authentication has become commonplace along with the popularity of mobile devices. There are many existing commercial 2FA solutions like the Google Authentication and the door system. Here is a common model for these solutions. There are 4 parts. The server, the encoded cell phone, the login device, and the user. When the user wants to log in online account, he first input the user ID and passcode. And after checking the ID and passcode, the server will send a challenge to the encoded cell phone. Then the user needs to respond to the challenge either through the cell phone or through the login device. This is an example. This is the door system used in our university. The first image is the interface of the browser, and the rest 2 images are interfaces from the mobile app. The door system provides 3 types of challenges. It may send a push request to the user, and the user needs to respond by pressing the approve button. Or the user may receive a call from the system and respond by pressing the pound key. For the last one, the user needs to copy a one-time passcode to the browser. As we can see from the example, the door system always requires user involvement, and other commercial 2FA solutions have the same drawback. This affects user experience and are not friendly for visually impaired person. Actually, our course Terry is visually impaired, and she always complains about the door system. Then can we eliminate user involvement from the authentication process? We found that in door system, all the 3 types of response can be considered as transmitting a 2FA response to the server. Then a zero effort scheme can be achieved by automatically generate and transmit the response. Considering the prevalence of a microphone and speakers, we want to use the acoustic channel for the transmission. However, without user involvement, the acoustic channel is vulnerable. There are mainly 2 types of attack that shatter the model: the co-located attack and man-in-the-middle attack. In co-located attack, the attacker is around the user, so the attacker's login device can receive the audios generated from user's cell phone. Man-in-the-middle attack is a remote attack. The attacker can record audios generated from the user's cell phone and relay it through a high-speed channel simultaneously. Now, before going to the detail of our scheme, I want first to illustrate the goals of our work. We want to propose a scheme that is usable. No user involvement should be required, but we do not want to sacrifice the security for usability. Therefore, our scheme should be robust against potential attacks, including the co-located attack and man-in-the-middle attack. Besides, the scheme should also be deployable. It can be easily deployed with commercial mobile device and standard web browser. And we want the scheme to be easily integrated to commercial 2FA solutions. We start our work by asking why the acoustic channel is vulnerable. We found that the risk mainly comes from 2 aspects. The first aspect is the ambiguity of audio source. The system cannot distinguish the audios from the user cell phone and the audio from the attacker's cell phone. And the second aspect is the co-located attackers. Then we try to find possible measures to address the risk. To solve the problem of ambiguity, the system should be able to identify different devices. And for co-located attack, we found that the attacker cannot be too close to the user, otherwise it would be noticeable. Therefore, we can do proximity verification. We measure the distance between the encoded cell phone and the login device. If the distance is larger than the threshold, then the request will be denied. With the combination of these 2 modules, we are able to propose a new scheme, proximity proof. We also add another module, 2FA response transmission, so that our scheme is compatible with commercial 2FA solutions. The first module is responsible for transmitting the response from the cell phone to the logging device using acoustic channels. And the second module can extract acoustic fingerprint for the cell phone. The last module can measure the distance between the cell phone and the logging device. Now I want to go to the detail of each module. In the first module, we use OFDM and on-off keying for the modulation. And we use the Reed-Solomon coding to deal with the transmission error. In our scheme, the response is transmitted in plain text. This is because for collocated attack and man-in-the-middle attack, the attacker does not need to decode the audios. Therefore, encryption cannot provide any extra security. We use acoustic fingerprint to identify different devices. Acoustic fingerprint is a frequency response curve of the acoustic component, like speaker and microphone. Here I want to use speaker as an example. The amplified factor of the speaker is different for different frequencies. Therefore, if we use a flight stimulation as an input, the spectrum of the output audio would be a curve. And since the curve is unique for each speaker, it can be used as a fingerprint. However, we found that it is not easy to extract the response curve for speaker. This is because we need to use a microphone to record the audios. In this case, the spectrum of recorded audios is mixed with the response curve of the microphones. As a result, we can only fingerprint the speaker and the microphone together as a pair. However, it cannot be applied to the 2FA scenarios, because it is very possible that the user wants to use a public computer to log in online account, while the microphone of the computer is not fingerprinted yet. Luckily, we found that the speaker and microphone are very common. The cell phone and the login device at least have one speaker and one microphone. Therefore, we can get more information about the component. If we let the cell phone and the login device both generate audios, we can extract a fingerprint for each pair of microphone and speakers. Further, we can extract the response curve for the speaker and microphone individually. This can be used for the fingerprint of the cell phones, and it enables us to distinguish different devices. For the cross-device ranging, we fully adopted the BIP method proposed by Chen Yipeng. I will not go to the detail of BIP. We adopted this method because it does not need synchronization between the cell phone and the login device. The acoustic fingerprint can guarantee that the encoded cell phone is presented, and the cross-device ranging can guarantee that the cell phone is very close to the login device. And then the combination of these two methods can verify the position of the encoded cell phone. Then we can make sure that it is a legal user that tries to log in online account. For the evaluation, we evaluate our system from two aspects, security and usability. For the man-in-the-middle attack, we first calculated the distance between the original fingerprint and the fingerprint extracted from replayed audios. We found that the distance is always larger than our predefined threshold. The threshold is calculated using F1 measurement. This means that our system can distinguish audio from different cell phones. And in totally 300 man-in-the-middle attacks, none of them succeed. The legal request can succeed with a rate larger than 98%, while for the collocated attack, the success rate is almost zero. For usability, we first measure the latency of our system. We found that the latency is always less than 2.5 seconds. Compared with the DOS system, the latency is very short. And also, we found that increasing the length of passcode used in our system does not increase the latency significantly. And here is the survey result of user experience. We can see from the result, most users think proximity proof is fast and easy to use. And compared with dual system, most users prefer our system. Now let's go to a conclusion. Proximity proof can be deployed with commercial mobile device and the standard web browser. And it is also compatible with the existing commercial 2FA solutions. Our scheme by automatically transmit 2FA response. Our schemes requires no user involvement. And the combination of acoustic fingerprint and cross-device ranging can guarantee the security of our system against the co-located attack and man-in-the-middle attack. Thank you.